Thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. We talk about phosphorus losses to the environment as coming from point sources and non-point sources. Point sources are those that typically come from the end of a pipe, such as the outflows of a wastewater plant to a river. Non-point sources are more diffuse in nature and are typically harder to manage. These would include things like erosion from agricultural fields. A new paper by Dr. Andrew Margenot of the University of Illinois at Urbana-Champaign and colleagues explores the major and underappreciated contribution to non-point source phosphorus loading that soil erosion from the banks of streams and rivers contributes. Crucially, measures typically prescribed for managing non-point source pollution in watersheds will largely fail to address streambank erosion. I had the pleasure of speaking with Andrew about his work and its implications. Okay, Andrew, thanks so much for joining us for Phosphorus Science Now. I'm really excited to talk to you about this great paper. Can you tell us a little bit about the article and your team?
Sure thing, Matt. Thank you for having me. This is an article that we published quite recently, and as you can see, it made the cover of JEQ. That's the image that you see, and the text on the right is the caption that the journal had to accompany this cover image. So this work was born out of a couple of convergent efforts. One was a statewide in Illinois effort to estimate streambank erosion and its contributions to phosphorus loads from the non-point source sector. And the other branch that converged with that was a special session that we held with our colleagues at the 2022 Tri-Societies meeting, which was in Baltimore. And the purpose of that special session was to get together in a room policymakers, scientists from diverse disciplines, hydrology, soil science, et cetera, to come up with a synthesis of what do we know about streambank erosion in general, and specifically in the Mississippi River Basin, the MRB. The focus of this is to understand what we know and what we don't know, and that's what we need to do to better understand how the erosion of streambanks influences phosphorus dynamics, and specifically phosphorus loads to surface waters. This is because, as you probably all know, the Mississippi River Basin has a phosphorus load challenge, and that impairs water quality both locally and in the Gulf of Mexico. Understanding the contribution of streambank erosion as a result is useful to have a more complete budget and balance of our P losses.
Great, that makes sense. And so who did you work with on this project?
Sure thing. So this project is a combination of, well, there's multiple entities. The funder is Illinois Nutrient Research and Education Council, Illinois NREC for short. They are a state-focused checkoff fund, and they were developed in response to the Gulf Hypoxia Task Force, where the EPA asked states in the MRB to come up with plans. So the funding mechanism to come up with research to help understand what can we do on our landscapes to meet our nutrient loss reduction goals. That's all facilitated by NREC. In terms of scientists, the session had over a dozen scientists and policymakers across the Midwest. And specifically for our research team, Dr. Shengnan Zhou in my research group is the key co-author on this work. So the full list of authors is shown here. As you can see, we've got folks from different parts of the world, like Dr. McDowell down from New Zealand, providing a perspective from that context. We've got folks who work in policy from state farm bureaus like Sean, to federal agencies like Dr. Boomer from FFAR. And specifically, these are the 3 team members in my lab that are really leading a lot of our phosphorus work, including on streambank erosion. Dr. Zhou on the left is the primary organizer and driver of this work. So I'd like to give some background on this paper. What you see here is an image that was the basis for the cover image of JEQ. And this was taken in December of 2021. That's myself on the left. And I'm looking at a lush bluff that was cut away, sloughed off by a small stream, and the stream is in the foreground. This is a pretty tall bluff. The folks up against the bluff on the right-hand side are fairly tall. They're about 6 foot tall. This is a 25, 30 foot tall bluff. And what we're trying to do in this work, in this field setting specifically, was understanding how much phosphorus is loaded into this small stream that then feeds into one of our most phosphorus impaired watersheds of Illinois. That would be the Embera. It is a Huck 8, and it has a phosphorus loading problem. This tributary feeds into it, and we were trying to understand the different sources of phosphorus, including point sources like wastewater treatment plants, and non-point sources like fields that get fertilizer that erode, but also stream banks, which are a non-ag, non-point source of phosphorus. To give you a bit more background on streambank erosion, it's important to understand that, well, in my opinion, streambank erosion is a very good representation of the terrestrial to aquatic continuum. There's transfers from soil to water. So streambank erosion is driven by the meandering of streams. Streams will change their course. This happens typically at superannual scales. So we're talking years to decades. And this is because water tries to find the lowest point in the landscape. So if you have especially flat landscapes, like in the northern MRB, like in Illinois, being so flat, there's not a clear winner of what the low point is. So water attempting to find that low point will meander even more back and forth. As it meanders, it will slough off its banks and carve out a new channel. Now, it's important to note that streambank erosion co-occurs with deposition, and that is what you can see on the bottom graph here. We've got the undercutting of the bank, but you've also got redeposition. This could be downstream. So it is part of a dynamic input and then export from the channel itself. All right, so a few key things to know about streambank erosion. It is a quintessential hot moment. All of a sudden, you get what's called a mass failure, where the undercutting of the bank will lead to a sudden collapse of the bank. So most of our P loads, or really the sediment loads that have the P, occurring from bank erosion will happen all at once. And the reason why we care about this process of banks eroding into streams when it comes to phosphorus is that, as we all know, phosphorus is present in all soils to some degree. This is from the parent material. This is an example of the time scale at which streambank erosion can operate. What we've done here is we've rectified historic aerial imagery of a river in the Sangamon of central states of Illinois. And by different colors, we've got different years. So by tracing the channel banks, we can see how over the past decades that the Mackinac River has been meandering quite a bit. And in that meandering, there's obviously sloughing off as well as deposition downstream. The takeaway here is that to get accurate measures of bank erosion and when it's loading into streams, whether that's carried downstream to the Gulf immediately, which isn't the case, or deposited hopscotch manner downstream, that process requires typically decadal timescales. Now let's talk about the magnitude. So biogeochemically, if we think about budgets or balances as a key technique to understand what's coming in and what's coming out, streambank erosion does become an appreciable magnitude. And at the state level and the MRB, it is pretty appreciable. So here's some numbers from Iowa State. If we think about how one estimates streambank erosion loads to streams, well, we first figure out the volume of sediment, or really the mass of sediment. So this is not unlike soil science, figuring out the volume. And then with the bulk density, you know how many kilograms or tons of sediment or soil are in question. And then by the total P concentration, we can multiply the mass of sediment by the concentration of P in that sediment and then derive an amount of phosphorus. So these are numbers that are based on estimates from Iowa State. I'll talk about that study shortly. And if we use their numbers, which is like Illinois, the magnitude of 17 million pounds of phosphorus thought to be entering into streams by bank erosion is pretty much what the Illinois Nutrient Loss Reduction Strategy, NLRS, goal to reduce P is. So the amount of P entering streams in our neighboring similar states is about what we need to reduce P loads by for Illinois. Because these states are similar, fair to say that we probably have a similar amount of P loading. So the point here is just to make clear that this is not negligible. There's quite a lot of phosphorus. Whether we can manage stream bank erosion to meet our P reduction goals, that's a different question that I'll touch on towards the end. All right, so let's talk a bit about non-point sources, because the focus of this paper in JAQ was to understand what are the implications of stream bank erosion for policy on meeting our nutrient loss reduction goals, specifically for phosphorus. Well, important to note that non-point sources, by definition, are diffuse. They're really hard to directly quantify because they're everywhere. So the way that we typically quantify non-point sources for phosphorus, including, is indirectly. We can measure the total phosphorus export from a state like Illinois through gauges. So the USGS has super gauges that are at the end of the watershed of the state. And we can do some math here, and they're able to estimate with fairly high confidence how much P is leaving the state of Illinois. Now that includes point sources and non-point sources. And if you subtract the point source, which by definition have a discharge permit, and so they have to report monthly data on P loads, we subtract the point sources of the states from the total export of the same states, and we derive the non-point source indirectly. Now, the problem is when we begin to equate non-point source with agriculture, as you can see, is being done by the Illinois NLRS on the right-hand figure. And so in this example, they distinguish urban in blue from point sources, which would include rural or urban point sources. So an ethanol plant, for example, or a wastewater treatment plant, doesn't matter, it's a point source. And note that rather than non-point source in green, it says agriculture. And this isn't quite correct because mathematically, technically, or sensu stricto, it is a non-point source. And this is an important distinction because there are different kinds of non-point sources, stream bank erosion being a prominent one for phosphorus. Another consequence as background of why we care about stream bank erosion for phosphorus balances and reductions is that, well, as you all know, total phosphorus doesn't tell you very much about the speciation, the kind of phosphorus in the stream bank entering the stream upon bank erosion. This is important because upon entering the water column or settling on the bed of the stream, the speciation of phosphorus will determine how quickly, or if at all, it will become dissolved reactive phosphorus. And that has immediate effects on local to regional to continental water quality. So for example, in this concept figure shown here, we might imagine that soluble phosphorus, which is a small fraction of the total, is immediately pulsed into the water column upon bank erosion. And that's why we see this immediate peak time after erosion of the bank into the stream. But then some forms like apatitic phosphorus, so calcium phosphate, may take a very long time to dissolve. And some forms like iron-bound P may go reductive dissolution, but then resorption depending on the anaerobic, aerobic fluxes in the stream bed itself. So this complicates our prediction of downstream impacts on DRP release. And this brings up a bigger biogeochemical point that is important to keep in mind, that there's going to be a buffering effect of these eroded bank sediments once they're in the stream bed. And long story short, there's a very dynamic back and forth where these stream bed sediments effectively buffer the amount of DRP in the stream water column. To put it concisely, we have now shifted the paradigm that rivers and streams are not passive pipes, conduits for P export, but they are bioreactors. They transform phosphorus. This is part of the lag effects of phosphorus engendered by stream bank erosion. This might have some of you thinking, well, is this what we hear often as legacy phosphorus? And the short answer is, yeah, it is in some sense. So legacy phosphorus is a term that has increased in use quite a bit. As we recently report in this ES&T paper, the terms of Residual phosphorus, which has its origins in agronomy going back to the 1920s, refers to a soil-based definition of phosphorus left over by a previous application. The idea is that something in the past impacts the present for phosphorus, what some call old or new phosphorus. What we're talking about in the case of streambank erosion is a watershed context. That term was first used in Florida in the late 1990s and has seen exponential increases, shown here in red, in the past couple of decades. So just to give out some definitions, we're really talking about legacy phosphorus, which is not necessarily derived from fertilizers. It's simply a past event that impacts phosphorus cycling in the present. The objective of this JQ study that we are talking about now is a simple question. How much does streambank erosion contribute to phosphorus loads in the Mississippi River Basin, MRB? And again, the focus is because, as we probably all know, the Gulf of Mexico, as well as local water quality in these MRB states, is compromised by P loads from point sources and non-point sources. So understanding the sources, including streambank erosion, can help improve our understanding of what's going on and how to manage that. All right, the approach that we took was to achieve a synthesis of the unknowns, knowns, and next steps, was to hybridize two things. First was a special session held at the 2022 Tri-Society's annual meeting in Baltimore, and there we specifically headhunted experts in hydrology and soil science and policy as well around the world, largely for the US, but other countries as well. And we had a mix of an open panel discussion as well as targeted talks to give a synopsis of what we know and what we don't know. At the same time, we also reviewed the MRB states nutrient loss reduction strategies or plans called NLRSs. Every state, or excuse me, most states in the MRB have such a strategy. And this is important because it helps us understand, on the one hand, on the left here, the science, and on the right hand, the policy, and if there's discrepancies between these. This is a topic where the policy doesn't quite reflect the science, including the unknowns and the uncertainty in the science. So let's talk a little bit more about the NLRS and how we extracted data from this. This is important for the paper. There was in 2011 what's called the Stoner Memo by Dr. Nancy Stoner. And this was a long, I think it's 5 pages, a memo that was saying, number one, there's a need for the MRB especially to reduce their total P loads as well as nitrogen. And so what is laid out in the memo is, well, states need to begin to organize to understand how much P, where it's coming from, and how to reduce it. And the second major point of the 2011 Stoner memo was that practices cannot be one size fits all. There are different sources and contexts of P losses, and so there has to be an overall framework that is then customized by the states. This is why each state is responsible for coming up with its own NLRS, following the basic framework put forward by the EPA. So if we looked at different states in the MRB, most of them have a NLRS. Here are just examples from different states. As you can see by the dates, most of these were put together in response to the 2011 Stoner memo within a couple of years, sometimes within 1 year to within 3 years. But by 2014, there was most states having some executive summary or some draft of a proposed NLRS. What did we find? Well, when we began with what is being described by the original NLRS, so the original plans drafted by states as far back as 2013 to 2015, what we find is that most states don't account for streambank erosion in their plans. They don't account for it as a P source in the non-point sector. Some states acknowledge it. No states actually quantify it, and some states don't even mention it, like the ones shown here with the red box, meaning there is a pretty large gap in the policy versus the science. So of the 31 states that sit in the MRB, 12 of these, which are the 12 states that are responsible for the majority of phosphorus, think of this as the Corn Belt states, basically, the Midwestern states. Of these 12 states that have a plan, only half of them acknowledge that streambank erosion matters for P losses. And this is oftentimes discussed as a potential target, but only by 5 states. So we're talking half or less than half think that it might be worth addressing. And recently, as of 2022, one state has now come up with an estimate, as published by Dr. Keith Schilling, of how much streambank erosion contributes in magnitude to statewide P export. And that was 31% of total P loads for Iowa are from bank erosion, which would be, if we normalize to the non-point source sector, that's 39% of the non-point source sector. So one state has data on this, and none of these state plans actually articulate or have an estimate. Now, we also looked at the updates, because these state plans that were all forged 2012 through 2015 have been updating, some every year, some every 2 years. And so across these different updates, as recent as 2023, we found that there is more acknowledgement of the potential contributions of streambank erosion to P loads. Now, 3 states now include the estimate. This is 3 out of 31 states, really 3 of the 12 that have a plan, to be more fair. And 5 states talk about how we might mitigate bank erosion. I won't talk about the complexity of how to stop the bank erosion, because again, it is a natural process. It can be exacerbated by how we manage water in ag systems. That's a different topic. But the point stands is that there is increasing policy awareness of the topic. That was a major finding of this paper. We also did a small case study for this paper showing the high variability and streambank erosion rates, but more importantly, I think, is the kind and the amount of phosphorus. Again, we care about the phosphorus speciation of streambanks eroding into streams because, well, that has consequences for lag times and when DRP is released downstream. So for example, we looked at the Polecat Creek watershed. This is the same location where the cover photo of that eroding bluff came from. And what we found is that at 5 locations shown here on the map, there were different degrees of erosion where, as we can see from figure B, green is minimal, not detectable, red is severe. And in the areas that were severely eroding, shown in panel C, the overall amount, the size of the pie chart differed slightly. And what differed more, though, was the speciation of phosphorus. And that would be shown by the different colors that correspond to the legend of panel D, from soluble in red, always a minor fraction, to residual, which was the major fraction. And that's the fraction that we define operationally by fractionation. The point is that that is not thought to be very soluble. So roughly up to half of our P could not be solubilized into DRP, depending on how you interpret this fraction. The point here is that the chemistry of streambank phosphorus is important to acknowledge, and coming up with accurate biogeochemical models on downstream DRP release. Okay. Some implications of this paper, which the paper discusses in detail, are as follows. Overall, if we don't distinguish the streambank erosion contributions to phosphorus losses within the non-point source sector, well, that means that we're going to incorrectly count that as an ag contribution, to the extent that we have non-point source synonymous with ag, as my home state does. So we found that these contributions, meaning streambank erosion to P loads, are relatively unquantified. No state officially has a quantification in the MRB. Iowa just came out with one. And they're also unaccounted for in policy. There are 4 implications of this that we go over. First is that, again, we're overestimating agricultural phosphorus contributions to non-point source P losses. Second, we're missing a chance to potentially manage a non-point P source. That could be valuable. Third, because of number 2, we might be misdirecting resources. So for example, resources for non-point source P loss reductions through things like cover crops that are in field may not be, in fact, will not address the streambank contributions. And fourth is that of lag times. And as well characterized by Dr. Darby et al. In 2013, there are different lag times of legacy phosphorus, and these can range from the order of months to even centuries. Streambank erosion is a major contributor to this legacy phosphorus that, as we can see from their figure in this paper, might be up to 1,000 years for when it's lost or, let's say, enters the waterway to when it leaves that system. This is important because it means that our expectations on phosphorus loss reductions across the MRB may not be realistic. It might take 100 years to see a drawdown, for example, in P loads, if a lot of those P loads are being driven by legacy sediments due to bank erosion. A question that we consider in the paper is, well, why is there this massive data gap? Why are so few states and such little science getting really good numbers on how much P and how long it stays in the system is coming from bank erosion? So our interpretation is that, well, it's really hard to get this kind of data. There are different methods like inserting bank erosion pins, as what Dr. Zhou is doing in the photo on the right. That's hard work, but erosion pins are a crude metric and they take decades of monitoring to get accurate data. There's also other approaches like remote sensing, but these have the disadvantage that they don't really capture small changes in bank. So we get trade-offs of scalability versus the accuracy, and we miss the first order, so the small streams that are thought to be the major contributors of bank erosion sediments. So if we look at the Illinois NLRS, because this is my home state, I think this is a illustrative example of why there's not much data and why policy doesn't really account for bank erosion just yet for phosphorus losses. If we look at the 2015 update from the Illinois NLRS, what they say is that the assessments that they have don't include stream bed or bank erosion sources of P loss because the data is not there. So at least they acknowledge it, but again, it's difficult to derive good values. So some recommendations that we came up with that are in this paper. First is that we need more field-based quantification. Modeling is okay, but there's not a lot of empirical data to inform good models. Second is one of disciplines. This might also explain why there's not too much data. Stream banks really are the interface of terrestrial to aquatic, quite literally. And as we explain in this paper, soil meets stream, we need to integrate different disciplines like hydrology and pedology to better get at this. And here's just one example, which we review in this paper in Geoderma. When we do stock assessments of, say, carbon or phosphorus stocks in soils, we do bulk density quantification to correct for differences in, well, the volume and the mass of soil. We also measure empirically total phosphorus. But typically, in most stream bank studies to date, people assume a total P value, or they don't even measure total P, they'll measure available phosphorus as estimated by, say, Bray phosphorus extraction. This means that we're not getting great numbers, and that's where hydrology can learn from soil science and also vice versa. A third recommendation that we make in this paper is that we need to go beyond the watershed P balance, which is an important step and a very useful biogeochemical tool, to drivers of bank erosion, especially stream flow characteristics. High flow events are likely to exacerbate or cause the mass failure, that punctuated event, the hotspot of bank erosion. But a balance alone doesn't really tell you much about how the balance is explained by, well, the drivers like high flow events. So an integrated approach that looks at P balances in concert with the hydrology and the workings of the stream is going to be important. Finally, complementary methods. Things like erosion pins are good, but they have their disadvantages and vice versa for other things like remote sensing. So we need to integrate methods. No one method alone for quantifying bank recession rates is going to work. Here too, there's a need for long-term studies. Because of the hotspot suddenness of bank erosion, studies should be going more than 10 years and preferably longer. That means setting up monitoring networks today to have good data in the next 20 to 30 years on this. And this brings us to benchmarks. Unfortunately, we need benchmarks to understand how current practices have exacerbated or mitigated bank erosion. This is where historical aerial imagery can be very powerful. So summary, I guess the last bullet point jumped to the end there, my apologies. We need to better understand non-point sources, the magnitudes and the types of non-point sources to better get a handle on our phosphorus export to the Gulf of Mexico. And here, stream bank erosion is an overlooked, both scientifically and policy-wise, source of non-point P loads. It's not acknowledged, as we show, in most MRB states' plans. It's not quantified in any plans. And furthermore, the science itself doesn't go all the way for high confidence P stocks, let alone the speciation of streambank phosphorus, which has very important implications for the lag times, i.e. legacy phosphorus. What are needs and next steps? Well, we need to go beyond the mass balance approach, important but not sufficient by itself, and understand the hydrology in concert. Second, we should be quantifying the bank erosion rates and P loads with confidence to, one, account for ag versus non-ag, non-point source contributions, see if we can maybe manage bank erosion or the sediments that have been eroded as a non-point source of phosphorus. Efficiently use resources for nutrient loss reduction plans or strategies across states. And I think most importantly for policy, have realistic expectations on drawdown rates of P loads. So this overall will require or necessitate an integration of hydrology, biogeochemistry, and soil science. And that's how we end this JAQ paper. Thanks for your time and happy to answer any questions. My email is my last name, margenot@illinois.edu. Thanks for your time.
Hey, Andrew, that was fantastic. And man, this is such an important paper. I really love it. It has huge implications, of course. You can go ahead and leave that last slide up.
Sure.
I wonder, speaking to the point of, I'm wondering how much we know about the change in stream bank erosion over time. So has it been increasing over time? And is that why we're having increasing phosphorus loads to the water bodies? And if it has been increasing, what are the main drivers of that? Is it conversion of land from wetlands, for example, to agriculture, or is it urban development, or what's the main driver of that? Do we know?
Sure. Just to clarify, Matt, you're asking what's the main driver of stream flow itself that can then exacerbate recession rates and bank erosion?
Well, I'm really just asking what are the main drivers of, if there's an increase in stream bank erosion. That'd be the first question. Has there been one over time? And two is then what's driving that increase? Is it land conversion? Is it something else?
Thanks for clarifying. So first question, has it changed over time? I don't think we know, because this is where having baseline data, temporally speaking, is really critical. But we don't really have erosion pin networks preceding the 1980s or 90s even, not to my knowledge. And then we can look at aerial imagery, as we saw for that Margenot River in the early slides, where it snakes from 1930s to present day. And that gives you an estimate of bank erosion rates. This is a big challenge, is that it's hard to understand. I think sediment cores can give us some insights to this. Now, that's not going to say, is it bank erosion or is it overland erosion depositing into the stream and then the floodplain or the lake bottom? So we don't know. There are probably indirect ways to get at that. I agree, that's really critical, because that would inform the answer to your second question, which is, well, your second question, I think, was, do you mind saying that?
Yeah, it was, what are the drivers? Is it land use changes? What is it?
Yep,
Whatever.
and so that would be useful for the drivers. And so I think these questions are interrelated. In terms of the drivers, absolutely that land use change can be a big driver. And if you think about the Midwest, it was tall grass prairie. By the 1890s, it was largely converted into agriculture. That was likely to have a huge effect on streams, as well as channelizing streams, digging ditches. We've drastically modified the hydrology of the upper MRB. That's not in question. There's an argument here, or there's a discussion to be had about what is a stream bank erosion rate like for a given land use, and do we care about that for policy? So if we're going to be using a lot of the MRB for crop production, well, that is going to modify the hydrology. So I think it's important to think about bank erosion rates pre-ag versus post-ag. What I would question is the utility of that in terms of informing policy. Unless we're going to go back to all prairie, I'm not seeing how that's useful for actionable steps. I think it's very useful, though, to think about how can we derive lessons from stream dynamics from native vegetation systems that could be used to design edge of field practices like constructed wetlands that would help buffer stream power coming off of ag influences. So for example, a topic here that we can't not mention is tile drainage. A lot of debate right now about what's the net effect of tile drainage on stream flashiness. The idea is that when it rains, do you see a flashier stream because of tile drains, or do tile drains smooth out the flashiness? And the evidence suggests that it can do both, depending on context, of course. And it's complex. There's been some recent work done and published that suggests that if you've got higher infiltration rate soils, tile drains lead to net flashiness, and lower infiltration soils, tile drains are better to reduce flashiness because they help reduce the runoff on the surface that would increase the flashiness. So it's complicated. This is one of the things that we are working on right now, actually, both modeling, lit review, and field assessments. I like your question, Matt, because it points to a greater need that this stream bank erosion process points to the need for a systems approach. This needs to be phosphorus science at the watershed scale that includes historical changes in land use and then integrating precip with ag land use with stream dynamics.
Sure. And am I correct then in saying that because we don't really have this historic perspective on stream bank erosion rates, we can't really attribute the increasing eutrophication we've seen in waters to stream bank erosion per se? Is that a fair statement?
I think in terms of high confidence causal link, I would agree with that. On the other hand, there's enough P entering these streams by bank erosion that I would hypothesize it's likely to help explain a lot of the downstream water quality effects. Yeah. And this is an example of a data gap as well. When you erode sediments, there's going to be some DRP that flushes out immediately. Then there's going to be slower release of DRP by organic phosphorus as it turns over, reductive dissolution of the iron phosphates, et cetera. So that question of how long and how much the DRP comes out of these eroded sediments, I think that's critical to understand in order to quantify what you just said. Is, well, how much is it actively driving eutrophication downstream?
Right. Yeah, it's fascinating. It's a great hypothesis, right? And a lot of research to come, I'm sure. And I'm really glad you're here to do it. So thanks, Andrew, again, for taking the time for joining us for Phosphorus Science Now. And hope to talk to you again soon.
Thanks, Matt, for your time. And again, happy to answer any questions that the audience has by email. Thank you.
Great, thank you.